Dear Mohammed, thank you so much for joining us on our scientific conference and for celebrating our birthday. I'm inviting you now to present us your research group and your results.
Thank you very much for this opportunity. I congratulate everyone for this 75th anniversary, and specifically Svetlana, thank you so much for the invitation. So I am Dr. Muhammad Yasir. I am from the Division of Microrobotics and Control Engineering of the University of Oldenburg in Germany. So I will briefly talk about all the different projects and activities that I am involved in my division. So Oldenburg is a city in northwest Germany. It's not as big as Belgrade. It's a small city, 170,000 inhabitants, and some key, since we are all talking about science and research, so some key factors that are noteworthy about the city of Oldenburg is that it was designated the City of Science in 2009, and there's generally a very big culture of startups and technologies and things like that. So these are some photos of the city, of the river Hunta and the downtown and the church. So just briefly, something about the university itself. It's named after Karl von Ossietzky, who was awarded Nobel Peace Prize in 1935. The university has several campuses spread out around the city. So the two main campuses are Harentor and Wechleu. It was originally established in 1793. It's, let's say, for European standards, a moderately sized university with roughly 16,000 students now, 2,600 employees, mostly researchers like me. There's a fairly good presence of foreign students and faculty as well. And we have a number of different projects, national, German projects, as well as a number of European projects. So now moving on to research and studies a little bit. So the focus of the group is mostly on nanomanipulation and design of different nano handling strategies. What I'm concerned about in the group is developing of sensing strategies by using microwaves, for example. But it's generally about designing infrastructure and technology for nanomanipulation, nano handling, and characterization of nanomaterials, and how to exploit them in devising sensing technologies. There's also some relevant courses that we are teaching both at the bachelor's and master's level. They are mostly based on microrobotics, handling, which is all relevant to the general, let's say, philosophy of the project, of the group, of the division itself. Yeah, and what I'm concerned about is microwave engineering and control engineering. So this is our group. The head is Professor Fatikov. We are 10 researchers, so the research staff is predominantly composed of PhD holders, so postdoctoral research scientists. They come from all different parts of the world, as you can see. There's a fairly big group of people working with microwave engineering. So we are mostly working on frequency selective surfaces, mainly on graphene-based tunable devices, scanning microwave microscopy, which involves also nanomanipulation and nano-handling of different nanostructures, all integrated into an SEM. as long as the collaboration is concerned and what our relevance is to the GrInShield project that Svetlana mentioned. It's mostly to give support about regarding microwave characterization and how to devise different strategies in order to improve electromagnetic interference and shielding effectiveness. We have also started working a little bit with EMI shielding, with biological applications, how to use radio frequency signals in order to extract relevant information from biological samples, like the detection of concentration of enzymes, for example, glucose in this case. So yeah, now I'll move on to the more technical subject, which for most of you, I hope is interesting. So graphene, it got a lot of fame because of a Nobel Prize that was awarded in 2010. So it's, as most of you might know, it's a single atomic layer of carbon atoms attached to each other in a honeycomb crystal lattice. There are different versions of graphene, monolayer graphene, multi-layer graphene, bilayer graphene, and so on. So the reason why it caught a lot of this interest was because of its tunable conductivity initially, because it could give it a number of different applications, and it was sort of looked at as replacement for conventional silicon technology, because since the power density on an integrated circuit was really becoming high and high, and we were looking, so there was a push for alternative to silicon. And that's how, this push into this research also from the EU really started, let's say, a revolution of research into graphene. But why is it interesting for us as microwave engineers and for electromagnetic interference and shielding effectiveness as well, is because the real part of the electrical conductivity of graphene can be tuned by the introduction of a voltage, by the introduction of a DC voltage. And as you can see on the top right plot, that this tuning is only possible in the micro and millimeter wave range. So from 3 gigahertz and up to 300 gigahertz. So in this frequency band, what we get is tunable conductivity. So the electrical conductivity can be varied by the introduction of a DC voltage, and this is what we are exploiting in most of our research. So something that is relevant to electromagnetic interference and shielding effectiveness is something that we are working on the side, are frequency selective surfaces. So why they are important is because they can be used in different applications. For example, radio frequency identification, like for example, the tag, when you go to open a door, you just hold a key or something near, like a card with an integrated circuit, and next to a lock, and then it recognizes it and it opens the door or something. So based on a similar concept, you can also identify different objects buried into the ground, for example, pipelines or different objects like that, which you want to trace. Another important relevant application is electromagnetic interference shielding. Antenna radomes. So radomes are devices that are protecting conductive antennas, the conductive part of antennas, from severe weather fluctuations or things like that. And in the design of reconfigurable intelligent reflective devices. So mostly, like most of the applications are designed around satellite communication and the detection of different objects in space, as well as how electromagnetic waves are interacting with the body and things like that. So what is a frequency selective surface? So frequency selective surface is a surface that is composed of different objects, different different objects which are referred to as unit cells. So unit cells have different areas where you can put different lumped elements like resistors, capacitors, and inductors, and then they behave. So they have they could behave as a reflective or absorptive or redirecting. So reflective means that the electromagnetic waves are going to the surface, and then they are totally getting reflected from the surface. Absorptive is when electromagnetic waves are going on the surface, and then you don't see anything back. They are all absorbed. And redirecting is when they are falling on the surface, and then they are redirected in another direction, or some of the aspects of the electromagnetic waves, like their amplitude, phase, or polarization is varied. So there's the incident signal, reflected signal, and transmitted signal. These are three key components. So what is happening until now in frequency selective surfaces is that most of the frequency selective surface used in satellite communication, for example, they are fixed. So there's no variation. And recently there have been a push to go in the direction of intelligent surfaces, which means that they would be able, so you do not have to change the surface itself, but change some parameter or an electrical signal on the surface that will change the response of the surface altogether. So there can be different means in order to enforce this change in the response of an intelligent surface or frequency selective surface. And there are two main controls. So one is electrical control, and another is mechanical control. So as of now, electrical control is happening by the help of resistors, pin diodes, and varactors. So all these three components are really bulky in size, and they cannot be integrated into a process of the fabrication of an integrated circuit. This is the big problem that needs to be solved. Mechanical control, as you can see, you have to physically move the surface itself in order to cause any variation in response of the surface, which is not feasible in most of the cases, because if you have to physically move the object, it involves a lot of different hardware that has to come in contact with the surface, like motors and things like that, which is not convenient in most applications. So what we are proposing is to substitute pin diodes, resistors, and varactors, which are bulky and big in size and so on, and not integratable in a semiconductor fabrication process. We are trying to substitute these components with graphene. As I said before, since graphene is electronically tunable, then all you would do is to somehow supply a DC voltage to graphene in order to cause an effect which will electronically tune the response of the frequency selective surface. So as I said earlier, the key component of an intelligent surface is the unit cell, which is one part of this whole array of different objects that are located on a frequency selective surface. This is an example of frequency selective surface that we designed as a part of a project funded by the German Academic Exchange. And what we did was we substituted graphene instead of the resistor and the varactor in order to cause this intelligent variation of the response of frequency selective surface.